Is my voice
Yes, sir.
audible to all of you? Okay, nice. So now I'll start. So, in the last class, what we have learned, we had learned about parallel plate capacitor. So we had derived the expression for the capacitance for a parallel plate capacitor, which has, let's see, whenever I talk about capacitor, you remember in the definition we have seen that the capacitor means there must be two conducting plates of equal magnitude of charge but with opposite sign. One will be positive, another will be negative. So this arrangement has to be there. Okay. So then we had derived that the capacitance will be epsilon naught A by D, which depends only on the geometry. A is the area of the plate, area of each plate here, each plate, and D is the separation between the plates. Now, today, what we'll see, if we insert, see, in the previous class, we have derived the capacitance for a parallel plate capacitor when I have air in between the parallel plate capacitors. Okay, there is nothing, no material is there in between these two plates. Okay, so in these two plates, in between these two plates, this space actually was filled with air. Air is also insulating in nature and some kind of dielectric material which has uh, dielectric permittivity epsilon naught. Now today what we'll do, we'll see the effect of the dielectric when we insert a dielectric material in between the parallel plate capacitor, what happens for that case. Okay, so how do we derive the expression for the capacitance for that case? Okay, so I am just taking the same parallel plate capacitor. Okay, same parallel plate capacitor, I mean to say the area is A and this is actually positively charged. Okay, positively charged, and it has charge density sigma. Okay, charge density means Q by area. Okay, charge, total charge on the plate by area, sigma, and this has actually a negative charge. Okay, same sigma but with a negative sign. Okay, negative charge by A. So this is the thing, and the area for this also same. And see this gap, the gap between the plates was D. Now what is the modification I have done? The modification is this, that this is now a dielectric material inserted in between. Dielectric material. Okay, and how do you characterize the dielectric material? With a constant C, or yeah, that is called dielectric constant. Okay, so this is epsilon E by epsilon naught. So this is how we define. So this is called epsilon naught. This is actually permittivity or absolute permittivity of the object, of the material, and this is free space permittivity, free space permittivity, and this K is called dielectric constant. Dielectric constant. Okay, so these are the things I know. And one more thing, see, I know the expression when nothing was there, only air was there. I know the expression for the capacitance. So if you have forgotten, I'm just writing for you epsilon 0 A by D. This we know. This generally we will say as C0. C0 means what? The capacitance of the parallel plate capacitor when the air was there in between the plates. Okay. So this is my capacitance. Now you have to tell me what will be my new capacitance if I say this as C, what will be my new capacitance? This is my problem now. So if you remember last time what I told, see sigma is given, okay. See dielectric constant is now given. See, uh, in the dielectric part, if you have not uh, noticed properly, I'll just tell you one more thing here, then I'll start the real derivation. This is also recap kind of. So if this is a dielectric material and I am applying external electric field through this way, this direction, what will happen, you know? Okay, I'll so if I apply electric field this way, along this way, suppose this is A, B, and this is C and D. So look, what will happen? This side will be induced with negative charges, and this AB surface will be induced with positive. I'm sorry, this is opposite way. This way it will be positive. Ah, I'm doing the same mistake. Sorry, this is negative because it is negative charges will go in the opposite way of the electric field. This is electric field, external electric field, and this is suppose these are the positive charges will be induced on the surface of the dielectric material. If this is a dielectric material, and look, I'll tell. See this the surface charges which is arising this side with a negative sign. I'll say negative sigma p, and this side I can say positive sigma p. P means what? Polarization. P actually indicates the charges arising due to polarization. What do you mean by polarization? Polarization means just separation of charges. See, dielectric material has no free electrons. They have both negative and positive charge strongly bound. So, so in case you don't have electric field, applied electric field, so positive and negative charges will be actually coinciding at the same place. They will be coinciding. So when you apply electric field, this positive and negative charges like this it will be, okay. This is the configuration. So they will just separate from each other and they will create a dipole, electric dipole. They will create an electric dipole. So when they create an electric dipole moment, you will find electric dipole moment. So dipole moment is nothing but Q into separation between the charges. So QD, and this by volume of the material will give you a term called polarization. This is polarization. In fact, the separation of charge is called polarization. Okay, separation of charges are called polarization. So due to polarization, this kind of charge will be appearing at the surface. Okay, and look, see, since there is a charge inside the material, see, separated. So electric field will be actually created. One electric field will be created. Suppose this electric field is E0, or I'll tell this is E0, and this is EP. Because of the polarization, this electric field is arising inside the material. So what is the effective electric field inside the material? So that will be external electric field minus this. Okay, I'll write in a clean space. So in the dielectric material, inside the dielectric material also one electric field will be created that will be opposing the external electric field. So what will be your effective electric field now? Effective electric field will be E0, that is the applied out applied or applied electric field, and this is the induced electric field inside the material. Now this will be your effective electric field. Okay, if you understood this thing, then things are very easy now. Now see, I'll just remove this part. Hope you will understood this. If don't, these are all written in the book very nicely, so you can just look back. Okay, now see what we are going to do. We are just going to calculate or derive an expression for the capacitance for this capacitor when I have kept on dielectric material inside having a dielectric constant K. So what you have to do, see, as I said, this is a parallel plate capacitor. What we have done, see, you have actually uniform electric field this way. Uniform electric field. Even even if you don't have this, see, in the in the earlier case also we have seen that in between parallel plate capacitor you will have uniform electric field. So that I can think of. Okay, these are actually, see, uniform electric field always denoted by parallel lines. My lines are not very parallel, but you have to assume that, okay, parallel equispaced line. So this is a field which I can think of this as E0, or the external applied field for this dielectric material. See, I know I know there is a relation between capacitor, uh, charge and voltage. Okay, Q is equal to C into V. Okay, now see, if, see, sigma I know already, so you can think that I know the charge. So I can see, if I can get the potential, okay, potential across this, then I can find out the capacitance. So now our aim will be, to find out the potential. So earlier cases we have seen that potential, see, potential again, potential actually related to electric field by this relation E into D with a minus sign obviously, but I'm taking the magnitude now. So this is E into D. Potential and electric field has relation E into D. So V is equal to E into D. Now if I somehow find out the electric field, then I can find out the potential. Then I can just divide with potential to get the capacitance. Okay. Look, when I say for a parallel plate capacitor, if my separation, see, this small d is much less than a, then I can think this as infinite plane. This plate I can think of infinite plane shift. So infinite conducting plate. So for that case, so I'll just remove this part also. So for conducting infinite conducting plane, so what we have got the electric field for that? We have got the electric field as, suppose this is E0 sigma by epsilon naught, right? This is when I have air, okay, no dielectric material is involved in that, okay. So sigma by epsilon naught, I have got that case, okay. So actually two epsilon naught for one plate, and for two plates it will be additive in between the region, in between, okay, region in between. So it will be sigma by epsilon naught. Now look here, I have to uh, find out whether this is epsilon naught or something else. Actually, that is not epsilon naught. So see, it has epsilon or epsilon naught k. Okay, in this case now. So this is the D. I know that. Okay, this is D. So if I know the electric field now, see what happens, as I told you that as you apply electric field externally, the dielectric material will be polarizing. So see, there will be uh, polarized charge, see, negative charge, polarized charge will go here, okay, and see here you had sigma already, now you have positive sigma over here, right? So here minus sigma was there. So you can see that now your modified charge density is what is your modified charge density now? Earlier it was sigma, but see, because of the polarization, see, here it will be here it will be minus polarization, right? Here, and it is attached to this, so this is connected to this, so that's why minus sigma p will reduce the sigma, okay. So earlier it was sigma, now it will reduce, okay. So now what is the modified charge density for the plates now? Modified charge density will be, look, if I say sigma prime, it will be plus minus sigma minus sigma p. Do you agree with me or not? This will be the modified charge density. So if you have modified charge density like this, then obviously you can find out the electric field. So electric field now, suppose A prime, so it will be what? It will be sigma prime by epsilon, not epsilon naught, because this material has epsilon, or you can write epsilon 0 into K. So this is the thing. Okay. So if you know that, okay, if you know this, see again one more thing. So this E prime is what? E prime is actually E minus EP, right? This is again E minus EP. This is the effective electric field now, right? Do you agree with me? Yes. So now look, I'll show you in your book that this, okay, look here. See now, my electric field, new electric field will be, okay, so this is, okay, they have kept, because they have considered this is sigma p, any no problem. So they have taken sigma minus sigma p by epsilon naught. Okay. So see now here this as I told, E0 is proportional to, see earlier we have seen E0 is proportional to sigma by epsilon naught, that means proportional to sigma. Now what will happen, this sigma will be actually proportional to sigma, this sigma minus sigma p, this will be proportional to sigma by k. Okay, if you don't understand, then I'll just explain it here. Okay, I'll just go to the next slide. So look, my new electric field, suppose E, okay, because in your book it is E only, so I'll write E. So I have applied electric field, and now I have this polarized electric field, internal electric field. So see, since this we have calculated, this E0 is actually sigma by epsilon naught. That means what? This is proportional to sigma, right? And for a linear dielectric material, this also actually proportional to sigma only. This also proportional to sigma. So what I can tell from here is that, so this also will be proportional to sigma minus sigma p, okay, sigma minus sigma p, or in other words I can write this will be proportional to sigma by k, okay, sigma by k, because sigma p also will be proportional to sigma only, okay, sigma p also will be proportional to sigma, okay. That's why, see, from this two, see, E is actually now here like this. So sigma p and sigma both are actually, see, sigma p, sorry, sigma p depends on sigma. I mean, this electric field depends on the sigma charge density, okay. Then EP also will be proportional to sigma, okay, because this is actually, this polarization depends on the external electric field, so, and that electric field depends on sigma. So this, both this, okay, just a minute. Oh, so look here. Oh, I'm sorry, actually I have uh, run into a problem where actually the screen got freezed. If you don't mind, I'll just take 5 to 7 minutes to restart the meeting again. Can you be with me? Can you just cooperate? Actually, my screen got frozen. Okay, I'll just take 5 minutes. Okay, so I'll just for the, yeah. So for now, I'll just switch. Yeah, I'll just end the meeting and then I'll restart the meeting again.
This conference will now be recorded.
Okay, so as I was discussing, the effect of dielectric, we'll just continue with that. Since I did not save the presentation, so now I have to tell you those things again. I hope you remember what I had written last time. So this has, see, after dielectric polarization, so this was positive plate here, Okay, this was positive plate. Now after dielectric polarization, here there will be minus sigma p. It was sigma p earlier, and these were connected. So the effective charge density here will be actually sigma minus sigma p, and in this case it will be minus of sigma minus sigma p. Okay, this will be here now, because this side it will be positive sigma because of the electric field, so which we have taken E0, like applied electric field due to the charge sigma. Now inside there will be effective electric field, which is actually say internal electric field or electric field due to polarization this way. And now effective electric field will be your this is E0 minus EP. What I was trying to tell you, that since E0 is proportional to sigma, now EP also will be actually proportional to sigma, as much as polarization, this electric field depends on sigma, and this polarization depends on E0. So in turn it is actually proportional to sigma. Again, see, because of this electric field only, this sigma p is arising. So I can tell that sigma minus sigma p also will be proportional to sigma. So what I can write now, I can write, I can write, see, the dielectric constant for this material is K. So what I can write, sigma minus sigma p is proportional to sigma by K. I can write this. Okay. Okay, proportional to sigma, so I can write proportionality constant as K. So I can write equal sign, sigma minus sigma p is equal to sigma by K. Are all, like, all of you could understand this or not? Can you tell me, this is a turning point here for this derivation? If you understood this, then everything is all right. Okay. So now look what I can write. I can write the new electric field. I can write the new electric field as sigma by K. So this you have to agree with. No, along with that there will be K0 obviously, because E was E minus E naught minus EP divided by sigma epsilon naught. This was the thing. Okay, and here again we had seen that this was sigma minus sigma p by epsilon naught, and sigma minus sigma p, which I have written sigma by K. So what you get now, electric field is this. See, these are few things which you have to understand. Okay, I hope you understood. Okay, okay, so I think I should not write this directly. I can write this one. Okay, I can write directly E is equal to sigma minus sigma p by epsilon naught. So which I can write, okay, which I can write like this. Now see, this is the thing. Okay, because this sigma minus sigma p depends on this. Okay, so if I know the electric field, now see, it is very easy. I have to find the potential. So E into D. See, this thickness is actually exactly the thickness of this dielectric material, exactly the gap. Okay, exactly of the dimension of the gap. So I can write E into D. So what is that? So it is sigma into D by K into epsilon naught. So once you get this, then it is, see, my whole calculation is done now. Then, so what I have to do, I have to divide this. Uh, so my C will be Q by V. Okay, understand? So this I have already got. Q, I can write Q, the original Q, that is sigma into E. So okay, so this is sigma into A, and divided by sigma D, and here it will go epsilon 0 into K. So this, so now look, okay, I'll just write it neatly. So this Q actually I'm taking the Q of plate only. So only thing will be here actually. Only change will be in the potential. So that I have already calculated. So this I will be keeping sigma into A only. Okay. And this from here I will be writing V as sigma into D by K epsilon naught. So this will go in the numerator, and see this sigma will go off, and see if I just arrange it, what I get is epsilon naught into K into this part. You look here, I know the C0, what I know is this epsilon 0 A by D. This much was my C0. So what I can write, see this K into C0 I can write. Okay. So see, if you want to multiply, like if you want to increase the capacitance of the capacitor, parallel capacitor, what you have to do, you have to just insert a dielectric material in between them. Okay, in between them, then you will get, see this is a multiplication factor now. This is the dielectric constant which you have got here as a multiplicative factor of the previous capacitance what you had when only air was there in between the plates. Okay, so this is how you can enhance the capacity of a capacitor. So when your C increase, that means what? It can hold more charge. That's why, see, the dielectric material has their application in the electronics where I need a capacitor. Okay, where I need a capacitor. Okay, where I need a capacitor. Like increase. So there inside the capacitor, parallel capacitor, we use the dielectric material. Okay, so that you can increase the capacity to hold the charge more. So when you have air, so that will be called air capacitor. Sometimes dielectric materials will be there. So according to the mica sheets or maybe some other dielectric material will be used for that practical purpose. So with this, the derivation actually gets over here. So I'll just show you in a book. It is exactly solved here. You just see this, okay, and you can practice by yourself and see this part in this box, rectangular box. Actually, this part is important to know what is polarization, what is displacement vector, what is displacement current, and what is the relation between electric field polarization and displacement vector. So this I'll be teaching you guys when I'll be teaching the displacement vector. I think in eighth chapter maybe, yeah. When I'll be teaching you electromagnetic wave, that time I'll be discussing this displacement vector. That time I'll teach you this portion. Okay. Now see, there is a problem over here, numerical problem. So see, I have what I have done here. I have see what I have done. I have only kept only one dielectric material. Suppose if I keep multiple dielectric material over here, or suppose one dielectric material of some thickness T, and rest of the portions I keep just empty like air. So I'm just going to solve one problem now. Look, the same parallel plate capacitor. Now instead of using the dielectric material of thickness D, now I have taken thickness T. So this was actually whole thickness was D. Now I have taken this as T, and D minus T, this portion is air. Okay, this portion is air, and this has dielectric constant K. Can you find out the capacitance for this new capacitor, parallel plate capacitor? This is again positive, as you know. Okay, this is negative plate, and this is sigma. This is minus sigma. This has area A. This also has area A. Can you find out the dielectric constant? Sorry, can you find out the capacitance for this capacitor now? Earlier, what I had done, I had taken a dielectric material of thickness D, but now I have taken of thickness small t. Okay, and rest of the portion I have kept air alone. So what will be the new capacitance? See, whenever I talk about capacitance and all, so what you have to remember, I have to find out the new electric field. Okay, what is the new electric field? Okay, or I can say new potential. Finally, I have to find out the new potential. See, in the earlier problem, what we have seen that this E is actually sigma by K when you have a dielectric material. Oh, sorry, sigma by epsilon naught into K. Okay, when dielectric constant is this. And if you have only air, electric field will be sigma by epsilon naught. Okay, now this concept I will be using. Look here, I have two potentials. Okay, this is in between in this actually V1 and this V2. So that will give you the total potential difference between the plates or in between the plate. So look here, I'll be having V1 plus V2. So what are V1 and V2? V1 I'll take V1 is this one. Suppose V1 and V2 this one as I have written here. So V1, how do I write V1 as I have written? So suppose this is here electric field is E1. Electric field is varying here. Okay, electric field is not constant everywhere now. Okay, it is varying. Okay, so the electric field will be up to T thickness some value. Okay, suppose E1T and E0T will be up to D minus T. So this is E1 inside the dielectric material. So what I'll write here is sigma by epsilon naught into K into T plus this one sigma. So this E0 is sigma by epsilon naught into D minus T. If you don't understand, please ask me. Okay, please ask me. Please put your question. Otherwise, I'll not be able to know whether you are understanding or not. Okay. So so is this okay? Is this okay to you or not? Okay. Look now. What we'll do? See, Priyadarshini, Kirtana, Mridula, Nikhil. Do you have any problem of this?
No,
You
sir.
can ask me. No. What about Kirtana?
No, sir. No.
Okay. So I hope Mridula is not saying anything means she also understood up to now. Can you respond to me, Mridula? Nikhil? Okay, hope you all of you are understanding. If you don't, if you can just ask me. Okay, I'll just continue then. Okay, so look now. So I'll just clean a bit here and then I can write it here. Okay, so see here I'll just do a little bit of simplification. So see, I'm just writing the total potential here. So which I have got like this. So I'll just keep my sigma by epsilon naught. Okay, sigma by epsilon naught common. So what I get here T by K, right? And then T D minus yeah, D minus T again. Okay, or if I just write in our little different form, so that is D minus T plus T by K. Okay, this is the actually very famous form of this. Okay, when I have more than one dielectric material, I'll just show you how to do that case. Okay, So this is C. In this case also you can see, think of more than one. That means two dielectric materials are there here. One is air, another one is of dielectric constant K. So now my capacitance will be what? My capacitance will be, the sigma was there, sigma into A divided by this, sigma by epsilon naught, right? And this will be D minus T plus T by K. Okay. So this is my capacitance. So see here, this epsilon will go up and then sigma go go up from both numerator and denominator. So what I can write is epsilon naught into A, epsilon naught into A, uh, yeah, epsilon naught into A divided by this term. Okay, D minus T. What is T? T is the thickness of the dielectric, like a dielectric material, one dielectric material. And yeah, so see, D minus T, this is air, and T by K, this is actually your dielectric material. Okay, now see, I'll just so this is the capacitance. So you have to remember this result sometime. This result, okay? What is that result? I'll just show you some problem. Uh, okay, suppose this one. If I tell you that there are n number of plates, okay? Sorry, n number of dielectric slabs in between the dielectric material, parallel plates. Okay, I'll just exactly read the problem. So suppose I have a capacitor. Suppose a parallel plate capacitor. I have n. Suppose this is T1. So this is T2. Then this is T3. Just a minute. I'm getting a call. I'll just attend that. Hello. 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 Yes. হ্যাঁ বলছি যে, হ্যাঁ বলছি আমি এখন একটা পড়াচ্ছি, একটু পরে ফোন করছি। Yes, so suppose I have, see, these are two parallel plate capacitor. Okay, two parallel plate capacitor. See, this I'll just draw. Yeah. Suppose these are two plates. Okay. Sorry. If I draw a little better way, so this is plate one, and this is another plate. Yes. Okay. This is another plate, and in between, suppose I have n number of slabs. Okay, n number of slabs of dielectric constant. Suppose K1 and thickness having thickness T1. This is K2 having thickness T2. Then K3 having thickness T3. These I have drawn almost equal thickness and equal thickness, but they may not be equal. Okay, here we are just guessing that they are not equal. So this is suppose K4 and having thickness T4, like that. This is Kn, dielectric constant. So for this case, what is the capacitance? So for this case, what will be the capacitance? How do you write? I think you people should tell me. You people can tell me what is that. See, I have written one thing. Just see. This is epsilon naught A for two dielectric material, D minus T plus T by K. Okay. So what I can write? See, from here itself I can write from this expression. So that's why I told you sometimes should remember this expression for your for your sake. So look here, D, let me take this as D. That doesn't matter. This is D as usual. So now look, instead of T, how many T's are there? There are see I have now D minus T1 plus, I'll just take a so T2 plus dot Tn, right? And you have again here, instead of writing only T by K, you have to write T1 by K1 plus T2 by K2, like that. Okay, if you want to do elaborately for each slab, that you can do, but you can use this formula itself to extend this formula for n number of slab as well. So see this, I can write Tn by Kn. Okay, so look this dimension, can you tell me T1 plus T2 plus T3 up to Tn, what will be the value of this? This will be the value of D, exactly D, right? Do you agree or not? So see, finally this term will get cancelled. Okay, so this term get cancelled. What you are left with actually, C is equal to epsilon naught A. A is the area of each plate. I suppose area of each plate is same. Okay, each is of them same. Okay, so then yeah, look, this term gets cancelled. So this term actually gets cancelled because T1 plus T2 plus T3 up to Tn, this itself will be becoming at D, okay, equal to D. So this D and this sum will get cancelled. What you get is T1 by K1 plus T2 by K2, like that you get up to this. So you got a formula for n number of slabs. Okay, what you have to do, you need to know the dielectric constant of each and thickness of that, and you just write epsilon naught into A, area of the plates, okay, in the numerator, and take the sum of this ratio T1 by T by K. Okay, you just write that and get the value. So this is actual capacitance for a capacitor, parallel plate capacitor, where you have put n dielectric slabs in between. Okay, so this is one part. And look here, okay, so yeah, so this is the thing. Okay, now what I can do is, actually this you can think, uh see, this is actually a series combination of various capacitors, you can think, series combination of various capacitors. So this combinations we will be learning again, uh series combination of all capacitors. So you can think of this is one capacitor, this is another, this is another, this is another, like that you can think of. Okay, okay, that I will see, obviously. So from here, at least now from here you could understand this, right? So if I take another one, look, uh okay, I think, see, in this case, you look the configuration, you look, so this is here actually, uh see, in this case also the thickness, see, each of them has thickness D, but the areas are different. Okay, A1, this has A2, this has A3, this is actually A4, and like that this AN. Okay, and all of them has different dielectric constant. Okay, like that it is Kn. Okay, so in this case you look, these are having actually different thickness, sorry, different area for all of them. Okay, different area, because my capacitor is now like this, but my these are, so these are my dielectric slab. Okay, so this is the area, right? This is the area. So this is the area is for each of them. But earlier what I had this thickness was different, but area was exactly equal to the plate area. Okay, now plate area is this, total area is this one. Okay, but see, each of them has how much area? They have separate area. This one, another one will be having this one. But see, the thickness is same. Okay, thickness is same. Now thickness, I can say the length of them is same for all of them, but only thing is area is different for all of them. Now see, this combination you can think of actually a parallel combination of the capacitor. So I'll just come back to this point uh, once I think, or I'll tell you here itself. Okay, this part I'll discuss again. once I discuss the series combination and parallel combination of capacitance again. Okay, this part I will come back to you later, but let me just okay. So since we have started at 6:10, I'll go another 10 minutes. Okay, if you don't have any problem, even I can go up to 7:15. You guys have any problem or any class like after that? You can just tell me, Kirtana.
No, sir, no. I
Can I go
don't
up to
have
10,
any
15,
class
7?
right.
Okay,
Yes,
so I can
yes,
go
sir,
up
you
to
can.
7:15, right? Okay. So what about I know Priyadashri and Nikhil, they are okay with that. What about Mridula? Mridula is not responding anyway. I'm taking her silence as like approval. Okay. So yeah, let us just read the combination part also. Combination of the capacitors. See, there are two kind of combinations as we have seen in case of our resistors. We have learned that if you have one resistor like this and back to back, if you just keep them, so this is A or this is B, if you just keep connect them back to back, so this actually is supposed to be a series combination. Okay, this is series combination. So what was the main fact over here? Look, the current is flowing like this, right? If this is a DC battery, this is positive terminal, this is negative. So current is flowing like this. So can you tell me what is common over here? The current. Current is common for both. Through both of them, the same current is flowing. That is I. Okay, that is I. But if I take combination like this, okay, and another one is like this, and connect with battery, now is the same current flowing through both? No. If this is I, so this will be I1, suppose this is R1 and this is R2. So in this way it will be I2, and here it will be combined I1 plus I2, that will come up here. So this will be again I. Okay, so here current is divided. This is called this why it is called current divider. Okay, current divider. Parallel circuit is called current divider. But divider, and this is actually, see here current is same, but I know, so potential, this is V1 and this is V2 across it. Okay, if this is R2 and R1, whatever. So here it is actually called potential divider. Current is not getting divided, but potential is getting divided. So this is called potential divider, series circuit. And parallel circuit is called current divider because current is getting divided to, like, divided into two branches. Okay, all right. So in this case, actually the potential is same for both R1 and R2. So potential is common, and in this case current is common. Okay. So similarly, if I have two or more than two capacitors, okay, suppose this has capacitance C1, this is capacitance C2, and see, this is positive plate, this is negative plate, this is again positive plate, and this is negative plate. So if you connect positive plate of negative plate of the first one with the positive plate of the second capacitor, then this kind of combination is called series combination. Okay, series combination. So this is series combination. So as I said, similar thing will happen according to the charge uh, conservation of charge. So this is series combination. So if I just connect with the battery, now look here, if I just connect with the battery, this is battery. So what will happen? What would happen? Charge will flow through this, right? Charge will flow. So can you tell me what is common? Sorry, what is common over here? Charge or voltage or potential? What is common through both of them? See, according to the conservation of charge, conservation of charge, what will happen? Whatever come out from the battery, that has to go through the whole circuit. Okay, that has to go through the whole circuit. That has to come through this as well. So the charge in both the capacitor will be the same. What is different? The potential across them will be different. Okay, potential across them will be different. Okay, V1 suppose, and this is maybe V2, like that. Okay, so if I then try to find out the equivalent, suppose this also Q, this is also having Q, this is C1 and C2. Okay, I suppose this is negative, this is positive. Okay, now if I have a battery V over here, connected to both. So look, the charge is same, means what I can write is actually, I can write Q is equal to I can write C1 V1, because the potential across this is V1. Okay, across this is V1 and across this is V2. Okay, so I can write again Q is equal to C2 into V2, or in other way I can write V1 is equal to Q by C1, and this I can write V2 is equal to Q by C2. Okay, so what is the total potential? Total potential is V. This I can write V1 plus V2. V2. So this I can write from here. Look, see, now this is actually uh, Q by C1 plus Q by C2. Okay, all right. Now if I just get a capacitor, single capacitor or equivalent capacitor, which I can connect across this same battery, okay, same potential, that means same potential, and it can store the same charge. Okay, I take C equivalent. I can get, instead of taking multiple capacitor, I'll just take only one equivalent capacitor, so which can charge which can store the same charge when I connect that capacitor across the same battery. So what does it mean? I can write C equivalent is equal to I can write, or I can write here V is equal to Q by C equivalent. I can write from this circuit. Do you agree with me? Okay. So see, I have taken equivalent one. So there also I have got the voltage V, and here also when I had used single components, I have got the voltage. Same voltage I have got. One is this and another one is this. So I can just compare these two and write, what I can write is Q by C equivalent is equal to Q by C1 plus Q by C2, that I can write, and this all charges are same, so they will go off. So I can write 1 by C equivalent is equal to 1 by C1 plus 1 by C2. So this is my equivalent capacitance. Okay, for a series combination. See, this is exactly opposite to the series combination of resistors. In case of resistor, what I get, R equivalent is equal to R1 plus R2, right? It will be exactly opposite. We will see in the parallel case, I will get C equivalent is equal to C1 plus C2. So this is the parallel case, right? In case of resistors, okay. In case of resistors, I get 1 by RQ is equal to 1 by R1 plus 1 by R2 for parallel combination, and in this case we get for series combination. Okay, now let us go for the parallel combination. So how do I write parallel combination? So this I have taken only two capacitors, but you can uh, extend this for n number of capacitors as well, which has been written in your book. You can just go through that. Okay, now what I can take, see, if I have a capacitor like this, having capacitance C1, this is positive plate, this is negative plate. Okay, now I take another capacitor C2, and see, if I connect the positive plate with positive plate, negative plate with negative plate, then this is actually parallel combination. This is parallel combination. Okay, this is actually parallel combination. So in this case, what is common? If I just connect this with a battery, you look, this is a battery V. So what is common here? The charge can get divided. Okay, maybe this is Q1 through this, and through this it is Q2, and total charge, suppose Q is flowing through that. Okay, so total charge Q is flowing through that. So what I'll write over here, I can write that the charge stored by C1 and the charge stored by plus charge stored by the capacitor 2, this will be giving you the total charge. Okay, as we do for parallel combination of resistors also, right, like this. So in the case of resistors also, we do, this is I1, this is I2. So in combination, this is I1 plus I2 over here, that is equal to I. So similar thing we'll be doing over here. Here the common is actually the potential, and the charge stored by both, if you take the sum of the charges stored by both, that will give you the total charge sent by this battery. Okay, so that is what we are going to do now. Again, we know the relationship, right? So I know Q1 is equal to C1 into V. Okay, this is the potential. Since both are across the same battery, so both of them have, see, this is A, this is B, so they have their terminals at the same terminals, positive and negative terminals are at the same place, so they are actually having same potential difference. So I can write Q2 also C2 into V like this. Okay, so now I'll just write total charge is equal to Q1 plus Q2, so which I can write this as C1 plus C2 into capital V. Now look, instead of taking these two components again in the similar way, if I just remove this two and take a single capacitor across the same battery, which can store the same charge again, Q, same charge Q. Okay, so what I can write here, I can write Q is equal to C equivalent into V. So see, this charge and this charge, they are non-different. Okay, so I can write then C equivalent into V is equal to C1 plus C2 into V. So V get cancelled. So what I get is, in a parallel combination, you have the equivalent capacitance, just sum of the capacitance. So you can just extend this up to n capacitors. Okay, so I'll stop the class today here with this lesson. So see, we'll be actually solving many problems. In fact, I just uh, prepared for that. I was actually planning to do that, since there was lack of time, I could not do. See, I have many problems sorted out. So these are the problems which you can. Okay, just a minute. I'll just tell you one for your flavor. See, if I have, suppose, this configuration, I have, see, 1 2 3 4 parallel plates. Okay, 4 parallel plates. Now if I just tell this is 1, this is 2, this is 3, and this is 4. Okay, this is 4. And see, the 2 and 3rd, they are connected with a connecting wire. Connecting wire and that, okay, connecting wire, and 1st and 4th, they are connected with another connecting wire to a point P. Okay, so 2nd and 3rd, they are connected with connecting wire to Q point and another 2. So you have to tell me what is the new capacitance of this capacitor. So there are plates, conducting plates, 4 plates are there, 1, 2, 3, 4. 2 and 3, they are connected to a point by connecting wires, conducting wires. Another 2, 1 and 4, they are connected. And so this arrangement is such that so all of them has the area A, okay, and the separation between all of them is D. So how do you calculate the capacitance for this arrangement of 4 plates? And see, it is actually in the air. So what you have to do, as soon as you get this kind of question, you just connect the battery with these 2 points. Okay, so this is negative point and this is positive terminal. Okay, this is negative terminal. So what you get, this plate 2 is negative, again plate 3 also negative. Okay, what you get for this, plate 1 is positive. What you get for the 4th one, again this is also positive. So how many capacitors you are getting? See between this 2 and 3, these both are negative negative. So for a capacitor to form, you need a positive plate and negative plate. So 2 and 3 does not form a capacitor, does not form a capacitor. Otherwise 1 and 2, they form a parallel plate capacitor having area A and separation D. Okay, and 3 and 4, they also form another capacitor. So you have two capacitor here, two parallel plate capacitor, and how is they connect? How are they connected? They are actually parallel because see both of them, see all the plates have the same at the same potential. Okay, at the same potential. So they are connected to. They are actually parallel. Okay, they are parallel to each other. So you can write here the result from the parallel combination. Okay, how do you write that? So these are parallel to each other. So if I say this has capacitance C1, this has capacitance C2, so what will be the equivalent capacitance or net capacitance? C1 plus C2. Okay, this is a problem which you will get in your exam, board exam, as well as your competition exam. Okay, competitive exams. Okay, this kind of problems will be asked in your competitive exams as well. So if I know C1, what is C1 and C2, these are both actually having same area and same thickness D and also air medium. So I can write epsilon 0 A by D for both of them. So if you just add both of them, so you get the total. So you get C is equal to 2 epsilon naught A by D. Okay, this is one problem. Another problem, see if they are cross connection, see this is 1, this is 2, this is, sorry, this I'll write 2, this is 3, and this is 4. Now also there are 4 plates, same area, same separation. Okay, same separation. Now what happened, see 1 and 3, they are connected to some terminal. Okay, and 2 and 4, they are connected to another combination. So now same thing, you just connect it to a battery. So what you get, this is positive terminal, this is negative terminal. Can you tell me how many capacitors will be formed here? Who can tell me? Kirtana, how many capacitors will form here? What about Priyadarshini? Can you tell me how many capacitors will be formed? You have to see the screen. See what is connected to what, you have to see, and then you have to give the polarity. So first one will be having positive polarity. So second one will be having negative polarity. Okay, so this side also you keep like this. See the third one also will be having positive polarity.
Fourth negative, sir.
Okay, positive. Fourth is negative, obviously. So how many capacitors will be formed? That is my question. How many
Sir,
capacitors
it's
will form here?
4, sir. 3.
Three. No, three. I'll tell you how. So this is one. See, positive and negative, right? This is one. This is one capacitor. This is another one. See, negative and positive. So here will be, this is second one, and see, positive and negative. This is third one. So there will be three capacitors. Okay, and so the capacitance will be 3 into epsilon naught A by B. Okay. All right. Nikhil, do you agree with me? Mridula, do you agree with me? Okay. So similarly, this kind of problem will come like, see, I'll just give you another example. Okay, let me go up. Yeah, I'll give another example. Suppose I have 1, 2, 3, 4, 5, 6, 6 plates. So how many capacitor can form here? 1, 2, 3, 4, 5. So if I have n number, so n minus 1 capacitor may form. Okay, n minus 1 number of capacitor will be formed.
Sir, 5.
Capacitor will form 5. Yes. Okay, so and see, obviously, yeah, so these are the things. So if they tell you that the n members are actually connected like this, so suppose in this case I'll just suppose I have 5 like this, 1, 2, 3, 4, or maybe 6, I'll say 6. So this is connected to your some positive terminal, and this is connected to your negative terminal. Okay, negative terminal. So see, this negative will be induced over here, positive. Negative will induce positive. This positive will induce negative over here. Okay, this negative will induce positive here. Okay, this is how actually the parallel plate capacitor will be created. Okay, do you understand? And this is obviously in this case this is also positive. So okay, so this kind of problem again I'll discuss on the next class. Okay, now for the time being we will stop the class. In the next class I'll take up this kind of problem again. Okay. Okay, see you on next day. Next day will be, I think, Wednesday. So yeah, so you read up to this, and then we'll meet again on Wednesday. We'll discuss many other problems like that. Okay then, bye.